Hello, welcome back. In this video, we'll continue to discuss the semiconductor lasers with special emphasis on heterojunction laser diodes and their characteristics. There are different configurations for the heterojunction laser diodes. In this video, we'll discuss the double heterojunction structure. We shall look at the construction of the heterojunction. The schematic diagram of the double heterojunction laser diode is shown here. The lowermost layer is the metal contact, followed by an N-type gallium arsenide. Over that we have the N-type gallium aluminum arsenide, and over that we have the gallium arsenide, and this gallium arsenide layer is the active layer. Over the gallium arsenide layer we have the P-type gallium aluminum arsenide. Since we have two different junctions here, we call it as a double heterojunction. However, the gallium arsenide is the active layer. Over the P-type gallium aluminum arsenide layer, we have the metal contact. These two metal contacts are used to bias the diode. We get the laser from the gallium arsenide layer. While discussing the drawbacks of the homojunction laser diode, we have said that the junction is not defined properly. While in the case of a double heterojunction structure, the junction thickness is well defined by the thickness of the gallium arsenide. Similarly, we have also seen that in the case of a homojunction laser diode, light can dissipate into the surroundings, while in the case of a double heterojunction structure, an optical waveguide is produced. So light is confined to the active layer. An optical waveguide is a structure in which the light is confined. Light will be confined and it is allowed to move along the length of the waveguide. In this case, light is confined between these two limits and it is allowed to propagate in this direction. The top and the bottom faces are metallized and metal contacts are provided to pass current through the diode. The front and rear faces are polished parallel to each other and perpendicular to the plane of the junction. The polished faces constitute the Fabry-Perot resonator. Now we shall see the working. The basic working principle of the heterojunction laser diode is similar to that of the homojunction diode. In the case of a heterojunction laser diode, the P-type narrow bandgap gallium arsenide layer at the center constitutes the active layer in which the lasing occurs. The P-type gallium arsenide layer is sandwiched between N and P-type gallium aluminum arsenide layers. Layer number 3 is P-type gallium arsenide. On the right side we have P-type gallium aluminum arsenide, and on the left side of the P-type gallium arsenide we have the gallium aluminum arsenide. The first layer is the N-type gallium arsenide, and these two layers, the N-type and P-type gallium aluminum arsenides, they have wide energy band gaps. When you have wide energy band gap, the refractive index will be low because the refractive index of high band gap materials will be low when compared to thin energy band gap solids. In the present case, the P-type gallium arsenide is having a narrow band gap. Since it is having narrow band gap, its refractive index will be high. It will be constant all across the third layer, and on either sides of this we have gallium aluminum arsenide whose energy band gap is wide. As a result, corresponding refractive indices should be lower. So on either side of the P layer we have the layers whose refractive indices are low. Since the refractive indices on either sides are low, the structure will form what is known as planar waveguide. The planar waveguide thus produced will confine light into the P-type gallium arsenide only. So we do not notice leakage of light into the surroundings. Now we shall look at the pumping mechanism. When the junction is forward biased, electrons and holes are injected into the active region in high concentrations, as we have discussed in the case of homojunction laser diode. When the diode current reaches a threshold value, the carrier concentration in the active region will rise to a very high value. Carrier concentration will rise to a very high value in the active region. The electrons injected from the N-type gallium aluminum arsenide layer into the P-type gallium arsenide layer confront energy barrier at the junction where P-type gallium arsenide and P-type gallium aluminum arsenide meet and are reflected back into the active region. Similarly, the holes are reflected by the potential barrier provided by the higher band gap N-type gallium aluminum arsenide layer. Thus, the layers in heterojunction structure confine the charge carriers to the gallium arsenide layer. The electrons injected from the N-type gallium aluminum arsenide into the P-type gallium arsenide layer confront energy barrier at the junction where P-type gallium arsenide and P-type gallium aluminum arsenide meet and are reflected back into the active region. Similarly, the holes are reflected by the potential barrier provided by the higher band gap N-type gallium aluminum arsenide layer. The heterostructure confines the charge carriers into the gallium arsenide layer. Therefore, the heterojunction confines the carriers to gallium arsenide layer. Now we shall look at the population inversion. Due to the forward bias, the active region contains a large concentration of the electrons within the conduction band and simultaneously a large number of holes within the valence band. Due to the forward bias, the active region contains a large concentration of electrons within the conduction band and a large number of holes within the valence band. The upper energy levels in the active region are having high electron population, while the lower energy levels in the same region are vacant. Upper energy level population is more than the lower vacant levels, because of which population inversion is achieved. Now we shall see the lasing. Spontaneous recombination of electrons and holes leads to spontaneous photon emission. This spontaneous photon propagating in the active layer stimulates the conduction electrons to recombine with the vacant states in the valence band and produce stimulated photons. The spontaneous photons propagating in the active layer stimulate the conduction electrons to recombine with the holes in the valency band to produce stimulated photons. The stimulated photons, now they reflect within the gallium arsenide layer because we have a planar waveguide established because of this structure. The stimulated photons, they reflect at the gallium arsenide air interface that provides sufficient feedback for laser oscillations. When the diode losses are offset by the laser gain, the laser oscillations will start. As the refractive index of the gallium arsenide is higher than the refractive index of the gallium aluminum arsenide layers, the light is trapped within the active region and it travels in only one direction. The wavelength of the light emitted by the P-type gallium arsenide layer is 800 nanometers when the band gap is 1.55 electron volts. The wavelength of the light emitted by the double heterojunction structure when P-type gallium arsenide is used as the active layer is 800 nanometers when the gallium arsenide band gap is 1.55 electron volts. There are certain advantages of the double heterojunction structure. The first advantage is heterojunction lasers have high efficiency even at room temperatures. Continuous mode of operation is possible even at room temperature. The operating currents are less than 50 milliamps. Output power of about 10 milliwatts can be produced. Now we shall look at the characteristics of the laser diodes. The characteristic curves of laser diode are shown here. Along the x direction we plot the current. Along the y direction we plot the power. So when the current is slowly increased, we notice that a threshold value is reached and up to the threshold value the optical power increases non-linearly, and beyond the threshold point the power increases linearly with respect to the current. The region from 0 to the threshold value corresponds to the LED operation or spontaneous emission operation. So up to the threshold current, the laser diode works as an LED, and beyond the threshold value, it starts operating as laser diode. In this video, we have started our discussion by understanding what is a double heterojunction laser diode. We have seen its construction, we have seen its working, we have seen how the refractive index helps to confine the light within the p-type gallium arsenide layer. We have seen the pumping mechanism. We have seen how population inversion can be achieved in the case of a double heterojunction laser diode. The lasing action, we have seen the advantages and the characteristics of laser diodes in general. Thank you.